Today, it seems we've already grown accustomed to the idea that the vast majority of matter in the universe cannot be observed through a telescope. 27% of it is incomprehensible dark matter, 68% is even more mysterious dark energy, and only about 5% is baryonic, or normal matter that emits light. This, it seems, is what the universe truly consists of. But if you think that scientists struggle only with understanding the first two components, you might be a bit surprised, as even these 5% of luminous matter raise many questions. When astronomers calculated everything that exists within galaxies, stars, planets, clouds of gas and dust, they found only 10% of the total amount of baryons in the universe. In other words, the vast majority of atoms of normal matter are not in galaxies, but somewhere else. But where exactly? Logically, this should be the space between galaxies. Searching for intergalactic matter is one of the greatest challenges of modern astrophysics, as it holds answers to key questions about galaxy evolution. In this episode, we'll talk about the mysteries of the intergalactic medium. The physical space between galaxies is generally considered very close to what we call a perfect vacuum. If you look for information about the average particle density in the universe, you'll find various estimates, but all of them are within the range of up to 1 hydrogen atom per cubic meter. However, the density of the universe is undoubtedly not uniform. It varies from relatively high inside galaxies, including structures like planets, stars, and black holes, to conditions in vast voids where particle density is several times lower than 1 hydrogen atom per cubic meter. Still, surprisingly, most baryonic matter truly resides in the space beyond galaxies. First, it's worth explaining what the term baryonic matter means. It refers to everything in the universe that consists, unsurprisingly, of baryons. That is, protons and neutrons. Yes, a typical hydrogen atom also contains an electron, which is a lepton. But in astronomy, this is usually ignored, as the electron's mass is negligible compared to the atom itself. So, when astronomers talk about baryons, they mean matter composed of atoms, stars, planets, comets, asteroids, clouds of cold gas and dust, neutron stars, and even black holes. Yes, black holes are included in the total baryon mass of the universe, as they still consume matter. But how do we even know how much and what there is in the universe? The answer lies in the concept of critical density. Simply put, it's the amount of everything in the universe needed to make it the way it looks now, that is, flat. In other words, it's the density of matter and energy at which the expansion of the universe will eventually stop, though only after an infinite amount of time. Based on measurements of the current rate of expansion, scientists have calculated that the critical density should be approximately 10 to the negative 27th kilograms per cubic meter, equivalent to about 10 hydrogen atoms per cubic meter. But even this small figure encapsulates the mass of everything, both matter and energy. So, what should the share of baryonic matter be? For the first time, a relatively reliable estimate was made in 1997 by 3 scientists from the University of California, San Diego. Their estimate of 5% was determined based on precise calculations of the deuterium to hydrogen ratio in the universe. In 2020, the most precise measurements of cosmic microwave background radiation made by the Planck Space Telescope confirmed this estimate. So, even by the most optimistic assessments, only 10–20% of normal matter in the modern universe resides within galaxies. However, this was not always the case. Much earlier, in the era when the first stars ignited, all baryonic matter was outside galaxies, as there were no galaxies yet. Hydrogen and helium atoms, like a mist filling the universe, represented all the normal matter. Slowly, under the influence of gravity, gas accumulated into denser regions and collapsed into the first stars, which eventually merged to form the first galaxies. If we still fail to find a significant portion of matter in galaxies, it suggests that their formation has been an inefficient process. After nearly 14 billion years of the universe's existence, most gas still drifts in the space between galaxies. The first clouds of intergalactic gas were discovered in the early 1970s thanks to the historic discovery of quasars. The thing is, intergalactic gas emits almost no light and becomes visible only when it lies in front of something bright. The spectra of quasars with relatively high redshifts, meaning distant and ancient, showed numerous such absorption lines, originating from hydrogen atoms. The principle is that a neutral hydrogen atom, which still contains an electron, absorbs energy in the ultraviolet part of the spectrum. The electron in the atom absorbs an ultraviolet photon and jumps to a higher energy level. If we understand quasars correctly, they must be supermassive black holes residing in the centers of ancient gas-rich galaxies and consuming surrounding matter. This matter, as it spirals inward, heats up to unimaginable temperatures, emitting light so brightly that it outshines the galaxy itself. Thus, the light from these distant and bright objects, traveling to us across billions of light-years of space, encounters numerous clouds of neutral hydrogen, which we now see as absorption lines in the quasar spectrum. If a telescope has high enough resolution, the spectrum can reveal hundreds of lines from hundreds of absorbers encountered along the light's path. This all resembles trees in a dense forest, which is precisely why it's called the Lyman alpha forest. The absorption lines, the trees of the forest, contain an astonishing amount of information about the intergalactic gas, including its chemical composition, distance, and therefore age. They also provide data on temperature, density, and the relative motion of gas clouds with respect to Earth. In fact, with the discovery of the Lyman alpha forest, astronomers gained a unique opportunity to study regions of the universe otherwise inaccessible to astronomical observations. One intriguing feature of quasar spectra is the presence of absorption lines that appear significantly larger than others. These suggest that the light encountered an enormous cloud of neutral hydrogen, possibly 1 million light-years in diameter. One such cloud was detected in 1995 by the Hubble Space Telescope, or more precisely, it was identified in the spectra of several quasars at once. Astronomers are still uncertain about the nature of these massive clouds, but one interpretation is that these structures could be precursors to galaxies. In any case, the Lyman alpha forest pertains not to the modern universe, but rather to an early epoch when galaxies were just forming. The biggest problem of the missing baryons is that in the present universe, neutral hydrogen cannot account for them. According to the European Space Agency, relatively cool intergalactic gas accounts for only 28% of the total baryon content. So, where is the majority hidden? One promising location for the search is the intracluster medium, the space within galaxy clusters, as well as the so-called circumgalactic medium. Although intergalactic and circumgalactic sound like separate terms, there is essentially no boundary dividing one from the other. The difference lies in the density, temperature, and chemical composition of the gas outside galaxies. The circumgalactic medium is, simply put, a galaxy's halo. Extended envelopes of relatively hot gas stretching far into space from the galaxy itself. The term hot genuinely means that its temperature is extremely high, ranging from tens of thousands to millions of kelvins. But how is this possible? Shouldn't the space outside galaxies be cold? In fact, the gas in the galactic halo is very diffuse. It is only 100 to 1,000 times denser than the average particle density in space. That means an average cubic meter of galactic halo contains 100 to 1,000 particles. For perspective, this is far less than the best vacuum we can create in a laboratory on Earth. So, while the galactic halo contains high-temperature hydrogen atoms, they are so dispersed that you would hardly feel any extra warmth if you were in that environment. From the perspective of a thermometer on your spacesuit, these millions of kelvins would not register in any noticeable way. But why does the galactic halo heat up to such high temperatures? This diffuse gas could be ejected by supernovae within the galaxy, originating from the stellar interiors. During the explosion, the gas is heated to extremely high temperatures. It's also important to remember that temperature reflects speed, that is, the velocity of particles in the medium, and many factors can influence this velocity. For example, gas can collide with streams of gas moving out of a galaxy, or it can be accelerated by magnetic fields permeating the environment. Additionally, diffuse gas cools very inefficiently. Atoms rarely encounter their neighbors and thus seldom transfer their energy. Even hotter gas found in the space within galaxy clusters can be fed by jets from supermassive black holes. These jets not only disturb and accelerate the gas, but also directly carry with them heated plasma from the accretion disk. The modern view of the circumgalactic halo is that it is closely connected to the galaxy's disk. The halo may play a critical role in feeding the galaxy with gas throughout its life and can fundamentally alter it. In other words, Circumgalactic gas and galaxies form a dynamic system that operates as a single unit. Stars and galaxies burn hydrogen, releasing light and heat, and after their death, they expel material into the interstellar medium and possibly even into the intergalactic medium. In this way, gas heated within galaxies enriches intergalactic space and gradually cools down. Cooling means that atoms move more slowly and the gas becomes denser. The galaxy's gravitational pull can draw this gas back, where it becomes fuel for the formation of new stars. The process repeats itself when stars explode, ejecting new gas enriched with more metals into intergalactic space. All these processes are poorly understood, and one of the main challenges of modern astrophysics is to comprehend the dynamics of gas between a galaxy and its surrounding environment. The challenge in studying circumgalactic gas lies in the fact that it is mostly ionized. This means the hydrogen is so hot that its atomic nuclei move separately from its electrons. As a result, such gas does not absorb light and therefore cannot be seen in quasar spectra like the Lyman alpha forest. Fortunately for astronomers, the circumgalactic medium isn't just hydrogen and helium. It contains significantly more traces of metals than the intergalactic medium. As a reminder, in astronomy, metals refer to all chemical elements heavier than helium. Unlike hydrogen, metals do not necessarily lose all their electrons under high-energy radiation. So, spectroscopic observations by Hubble and the X-ray Newton Observatory have detected absorption features from elements like carbon, oxygen, silicon, and iron. If metals are synthesized in the hot cores of stars, it logically follows that the gas around galaxies is somehow connected to the galaxies themselves. All these halos of diffuse hot plasma must play an important role in the life and evolution of galaxies. Unfortunately, the dynamics of matter exchange between a galaxy and its surrounding environment remain poorly understood. Observing these processes is extremely challenging, as the gas is diffuse and its emission is difficult to distinguish from the galaxy's own radiation. Therefore, only a new generation of telescopes capable of observing the universe in ultraviolet and, most importantly, in X-rays, will reveal new details about how galaxies breathe. Alright, but does the hot plasma in the circumgalactic medium, as well as the even hotter plasma in galaxy clusters, explain the missing baryons of the universe? Indeed, stars, galaxies, and their clusters are concentrated in the nodes of the cosmic web, a filamentary distribution of dark and ordinary matter stretching across the universe. While these nodes appear relatively dense, they are actually quite sparse compared to the surrounding space. According to data from the European Space Agency, only about 5% of the universe's baryons are found in the hot circumgalactic gas, and hot gas in galaxy clusters accounts for just 4%. This means that the majority of normal matter is still hidden somewhere. There must be something else in space. In 1998, a supercomputer simulation was conducted to model the universe on its largest scales for the first time. The cosmic web emerged as a network of glowing filaments connecting enormous structures made up of tens of thousands of galaxies. These luminous elongated objects, known as filaments, are predicted by astrophysicists to also contain diffuse gas. Filaments stretch for tens of millions of light years and are estimated to hold about half of the universe's baryons in the form of hot, diffuse gas. This gas has a temperature ranging from hundreds of thousands to millions of kelvins, and its density does not exceed 100 times the average density of the universe. Astronomers refer to this as the warm-hot intergalactic medium, WIM. Due to its low density, observing it is extremely difficult. Its thermal radiation is very weak, even fainter than that of the galactic halo. Thus, the cosmic web remains predominantly a computer model rather than an outcome of direct astronomical observations. The predominantly ionized hydrogen in the WIM cannot be detected in the Lyman alpha forest. However, this medium should be enriched with metals ejected from galaxies. In 2010, using X-ray telescopes like Chandra and XMM Newton, scientists detected absorption lines of ionized oxygen in regions where models predict the presence of filaments. Nevertheless, the best evidence for the existence of the warm-hot intergalactic medium does not come from quasars. In 2007, astronomers discovered strange astronomical phenomena known as fast radio bursts, FRBs. These events last only a few milliseconds but release an astonishing amount of energy. The mystery lies in their unknown origin. astronomers know only that these short radio pulses originate from distant galaxies. Despite their enigmatic nature, FRBs have played an unexpected role in the study of the intergalactic medium. The key is that as a fast radio burst passes through clouds of ionized gas, different frequencies of its radiation are slightly delayed by this diffuse medium. This phenomenon is called dispersion, which also causes white light to split into a spectrum in a prism or raindrops. We'll discuss dispersion and light refraction in detail in future episodes. In 2020, a scientific paper measured the delay in FRBs and used it to determine the presence and quantity of matter along the radiation's path. Finally, astronomers obtained significant confirmation that there is indeed something in the faint, distant cosmos, matter that cannot yet be seen with telescopes. Based on the dispersion from 6 fast radio bursts, scientists estimated that the amount of baryons in the filaments aligns well with theoretical predictions. The warm, hot intergalactic medium contains the majority of the universe's normal matter. Unfortunately, studying this medium still requires new generations of X-ray telescopes. No one knows for sure what caused gas to escape from galaxies, whether it was black holes or the explosive winds from stars blowing heated gas into intergalactic space. It is also unclear where the ejected gas ends up, whether it remains within the galactic halo or spreads much further into the intergalactic medium. In fact, evidence exists for both scenarios. What astronomers are certain about is that galaxies either thrive, actively forming new stars, or they do not. And at some point, their star formation mysteriously stops in a process known as quenching. Thanks to the largest sky survey, the Sloan Digital Sky Survey, astronomers have classified galaxies into 2 main categories: blue galaxies, rich in gas and actively forming new stars, and their opposites, red galaxies. Red galaxies are gas-poor, with almost no new stars being born. Strangely, very few galaxies exhibit intermediate properties between red and blue, meaning most galaxies are either alive or dead. This suggests that the process responsible for quenching occurs very quickly, over the course of just about 1 billion years or so. But what exactly is this process, and why do galaxies quench so rapidly? Even more puzzling is that numerous studies of galactic halos, including those conducted with the Hubble Space Telescope, have shown that gas exists even around seemingly dead galaxies. This gas has temperatures ranging from tens of thousands to hundreds of thousands of kelvins. At such temperatures, the gas should, in theory, fall back into the galaxy, replenishing its supply. Yet this does not appear to happen. Something either blocks its inflow or heats it to a temperature that prevents it from falling in. The data we currently have is just a handful of fragments, offering no clear answers to these fundamental questions. As a result, we still lack a cohesive picture of how galaxies live and evolve. Why is this so important? Stars are born from cold clouds of neutral hydrogen. During their lifetimes, they process this material and, upon their deaths, eject large amounts of metals into space. This matter may return to galaxies, giving rise to a new generation of stars. Around these stars, protoplanetary disks form, condensing into planets, one of which gave us the chance to be born. Thus, the story of where baryons are, how they evolve, and how they move through space is not just the story of galaxies. It is also the story of how and where we came to be.